do, but basically think of it as this. Say this is you're trying to balance this. This system is nonlinear. It's very hard to balance it. There's actually models and ways to do that and actually have it so it stays upright no matter where you tell it to end up. So that part of my summer research was actually looking at actually learning AI and then applying it to such models so I can then go and give it to our students. So for nonlinear parameter estimation, which is what my main field is, I do not have timing, and for some reason the timing is one of my slides. Is say we have this big aircraft. This aircraft costs $20 million to build just one of them. But we need to update those systems every once in a while. Well, how do we then test them and redesign in a lab? So part of what I'm trying to do is say, okay, when we're in this system and this system, we actually don't know what actually goes into the model. Whether it's just a single spring or if it's a spring that reacts differently. Is it what's called nonlinear snapper, where they have this paper and it's like this. And all of a sudden it vibrates and it's now in this position. How do we actually combine all of those? I'm an experimentalist, so I'm looking to try and get the best data as possible from here to people that are building these models to actually be able to make these as accurate as possible so we can cheapen building this and the thing blows up in the sky. So we don't want that to happen when there's loss of life possibly. So for nonlinear parameter estimation, it actually, in the United States, there's $2.5 billion actually spent every year on it, with $2 billion just in testing, because a lot of times we actually don't know, we don't understand what's going into it. So one of the things in a lot of these systems are what are called joints, so bolted joints and all that. We actually don't actually have good models for those. So a lot of my focus in my research is on bolted joints. So the simplifications that are used a lot of times is these joints are just forces. So this whole joint here holding these missiles is just modeled as what are called point forces. Basically thinking, okay, these joints are just this. Well, that's not actually how they really react. There's other forces in there. There's elasticity in the boundary. So my finger pad is squished. That actually is different. And then another part of this is the actual boundary condition. A lot of times, so we have this, and then we're saying these two shakers right here model it perfectly. If I'm able to exactly control it, it's exactly modeled correctly. That's not correct. So just in general, there's many types of nonlinearities, and each of them comes with their own unique challenges for testing. So we have joints. So we have two actual systems that are bolted together. As you're actually testing them, eventually, instead of being like this, they'll end up cocked from each other. How do you account for that? How do you tell that to the model to update for that? Then we have the geometric, the one that I showed with the piece of paper here, where it's very thin, and then all of a sudden its orientation changes. And then we have material. So every material, at some point, it changes. So think of rubber. Metal eventually starts reacting like rubber. So you have that type of nonlinearity. So how do you program that into models? So say aircraft wings, which a lot of times are actually designed to flap some as you're flying through the air. If you're afraid of flying, do not sit in the back of an airplane and look out the window, because you'll actually see the wings flexing. And it's actually studied on the big aircrafts, those wings flex almost 3 feet up and down. And as you use the fuel in the plane, that vibration gets even bigger and more visible. So just in general, the safest place to sail on a plane is over the wings, because that, yes, it's where the fuel's stored, but it's also the most structurally sound. So if anything happens to the plane, that area more than likely is staying whole. So just a little tidbit for when you're booking your next flight, okay? So the other thing overall is there's no consensus on how to actually measure this. I've been looking at what's called step sign control, and recently I've started moving into what's called phase lock control, and that's because there's two different fields of study. One's a lot of it is from Sandia versus Stuttgart over in Germany. And now we're trying to merge all these together and trying to find the best way to actually experimentally calculate this. And then just generally overall, this is a solid beam here. It's supposed to act linearly. The whole system, though, with how I have it, I have bungee cords. Bungee cords are rubber bands. As you stretch it, it gets harder and harder to stretch. So that's a nonlinearity that's been introduced in the experimental. So how do we want to deconvolute that? So again, I'm just trying to capture the best data to give to modelists to actually go and make these models as accurate as possible. So just overall, some things that are important for me to take into consideration is just the overall shape of the nonlinearity when machining. This is actually a beam that we were testing with at Sandia. The wire EDM actually snapped while it was cutting, and then they can replace it and continue cutting. You actually, if you run your finger over this, the actual beam, you don't feel it, but it's visibly there. And at the end of the day, it actually turned out that you can see it on what's called the pressure, the contact pressure. So how everything sits together. And then we have the nanoscale disparities. This noisy signal here, it's actually all the ridges that are on there. You can't see it by visualization. But imagine this with another one sitting on top of it. At some point, these will actually lock together and prevent motion. So it's a higher level of friction. And then just overall, these are 4 different beams, exact same test. They're highly variable. So how do we even start making controllers or testing and saying, hey, this is our beam, but this peak right here, as you're seeing, disappears, or it's there. What do we do? So we have many different experimental techniques, such as hammer, shaker, and shock. Hammer and shock, they're nice, but they're typically single one-off things. Shock is actually a destructive test. It's put into this tower that's 20 foot tall, that has 3-inch thick bungees. Those bungees are stretched, and then in those 20 feet, the thing accelerates to almost 70 miles an hour before it hits the ground. So very destructive. And typically your parts won't survive that. But then you have shaker. Now that's what I'll be looking at. Most of my studies are for here. But the main issue is once you start using a shaker and you add a controller, you actually start shaking the system at resonance. So as Mike said earlier, the Tacoma Narrows Bridge, that was essentially being shook by its own self-resonance. So do you want to actually introduce that into your system? And again, you're changing the dynamics of your system with it, so are you actually giving the modelist the correct information? So, AI in nonlinear dynamics field, a lot of it is in robotics. So, the robotics control, the self-balancing pendulums, all of those. There is some use in vibrations and noise reduction, but the only papers I could find for this were using known models and saying, hey, there's excess noise on this. Get rid of the noise. I don't care about it. So it's artificially changing the data set. So that's not good for giving to the modelists. And then other ones are on control parameter optimization. So in those controllers, we have what's called a plant, our actual system, and then the model. So a lot of controllers are based on knowledge that you know what you're actually controlling. So AI is being used to update this model and the controller at the same time to be able to control the system how you want it to go. Now that works very well for robotics because this is a very rigid part. So it's really easy to say, okay, this is how it will move through space. But that's not what I want to do. I want to know, okay, I don't know what the model is. So I actually, using some general information, I was actually able to find that there's an AI demo in MATLAB for the inverted pendulum. So I went and recreated it. So there are different fuzzy logic systems. There's the Mandano and Sugano. The Sugano is very numeric based. So basically what this controller is right now, where Mandano is more of a, hey, it's natural language. So like, hey, if this part is moving this way, do this, select this curve right here. If it's moving at, or if it's moving at this, if it's at this angle at this speed, select this one. So that it's more language based. So with that, I actually created a little simulation of what I did. I had to make a video because I tried running this on our new Azure clients, and just this loading took 5 minutes to do. So I was like, oh, wait, how should I do this? He's like, do a video. So as you can see, it's moving through space. And then right at the end, I showed that I didn't actually just make the animation for the pendulum to just move side to side nicely. Actually, if you click too fast on this, the controller actually starts to break down eventually. And their pendulum goes falling. So eventually you can get it to fail. Now I didn't actually sit and optimize the control parameters for this because I was just trying to learn it generally, and I got to the point that I think I can now teach our students this to a better degree. But if you actually run the MATLAB one, no matter how fast you program it, the pendulum may sway just a little bit, but it'll go and stay vertical right to where you tell it to go. So it looks like it's just a vertical line just moving back and forth. So how can AI help? So when you add controllers, as I was saying, you cause resonance in the system, which you typically don't want to do. However, for testing, you take discrete data sets. So say this is our data set right here. It's just a sine wave that I generated at a certain level. And we're zoomed in here. Now I take the RMS value of these specific locations. Then you can see the root mean square value, so the average of those is alternating. If I'm trying to control the amplitude, that actually causes issues. Now, if it's low, it wants to say, okay, raise the amplitude. If it's high, it says lower. Fuzzy could actually help, I believe, with slowing that down because it smears it out. Where the actual hard PID controllers, they're like, okay, do this. No matter what, do this. We don't want that to happen. Now, in current work, I'm starting to make the program for making these controllers in MATLAB. I'm having issues with it actually adjusting the frequency, but that's where I currently got to, which is why this is a nice looking control loop, because I'm just trying to get the team to just change this sine wave that is being generated. So in conclusion, AI and nonlinear dynamics, mostly robotics, but it can be used in other ways. Future work is continuing to build that controller so I can actually run the experiments here. And then I'm going to use this in courses. I'm going to introduce this to our freshman mechanical engineering students because I created a programming course last year. And I teach them logic, so now let's add the fuzzy logic to it because they're still starting to learn stuff. So I think I could get it without them being too confused. And then also I have a control systems class that I teach. So this year I'm going to have it as an extra credit project that they could actually go and optimize my inverted pendulum so it reacts properly. So they start getting their hands on actual controls. And I don't know if there's much time, but if you have questions, I'm more than happy to take them out. Thank you. Thank you so much.